Anyway, yeah, thanks, Norbert, for hosting, inviting me, and being the last man standing of the hosts. Yeah, so I wanted to talk about something, sort of my attempt to think a little bit about actually using tensor networks. It's very fun to theorize about tensor networks. I guess we're all sort of doing that this week. But at some point, you want to actually use these things. And lacking the skills to actually use them, I decided to theorize about how useful they might be. So I'm going to talk about stability, topological order in a tensor network. PEPs to be more specific. And there's a bunch of work that's already been done on this. Actually, some of the earliest work understanding how you represent topological states in tensor networks. So I should give this a also talked about the stability problem. And today, all right, well, let me motivate it first, then I'll give you an outline of what I'm going to say. So the main question is, given some tensor A that I'll draw like this, and I'm going to stick to 2D for a while and then move to 3D. Let me draw pictures as 2D. You make some tensor network state out of this on periodic boundary conditions. So, repeating it. Everything I'm going to talk about is kind of translation invariant, using the same tensor everywhere. Up. And this gives us some state that I'm going to call A. A is every vertex. And imagine, we represent some topological ground state with this tensor network state. And we want to ask if we take some other tensor, add some small perturbation in the generic form, and make this network. So this is like my notation. I guess I should have like L by L, but I'm going to just be sloppy. We take slightly perturbed tensor and put it on the same grid. Does this have the same order as this ground state? Okay. And maybe some of you already know the results on this. The answer is basically no. That was already sort of shown in this paper. And it comes from an interesting fact of how the relationship between local operators on the physical and virtual space, which I'll explain. But that's sort of the motivation. We want to understand when does this have the same order as the version of the tensor. And I'm going to talk about, starting with going into this example from this paper a bit more in depth. And then the new results, I'll move on to code PEPs 3D and see some different things happening, which are kind of interesting. And I guess I probably won't maybe I'll say this. What happens for general NPO injective? Okay, good. So let me start at the beginning. I'm going to introduce some basic tensors that I'm going to build the Torah code ground state out of. Maybe this is very familiar, so you can go to sleep or do something else for a little bit if you're used to it. I need this delta tensor. I'm going to draw like a solid dot. And that's just given by a delta function. All the indices are equal. It has a bunch of symmetry properties. So you basically multiply all of the indices by x's. And let me go like this. You also multiply pairs of z's, and any way you like. Any two pairs, only just a regenerating set. And that will leave this tensor invariant. That will give you all of them. Okay. Good. And I need another tensor, which is like the dual basis to this one. This guy is just given by the sum of these mod 2 being 0. those are the two basic tensors. Let me show you the symmetries of this one, then I'll ask you one of these questions. So this one's in the dual basis, so it basically has all the same symmetries, but swapping x and z. And at various points in the talk, I might use the same tensors with more legs. Hopefully that makes sense. The definition kind of generalizes to an arbitrary number of legs in an obvious way. So what is this one? Should be pairs of x's and z's everywhere. Good. So those are the symmetries of that, and they're related by changing basis. So let me just draw that basis change relation. This Hadamard is just like my notation for the matrix that swaps me from the x to the z basis. All right, so really I have like one tensor in a Hadamard. That's what I'm working with. Okay. And, all right, let's talk about the Torah code. So Hamiltonian, you've seen it a few times already. Let me write it down for completeness. Qubits living on the edges of a square lattice. So this is not a tensor network picture. This is like an operator in physical space. And I'm going to use this basis. So the vertices are x's, duplicates, z's, everything commutes. And in torus, you get full ground space degeneracy. It's not going to be too important for purposes of this talk. And if we use these tensors, we can easily build the ground state of this by a trick where you basically take some input state and project onto these terms. I'll explain that, I'll show you the result. All right, I might need to make a good picture of this to use it a few times. All right, so what's our ground state? Basically, on every vertex, I'll put this x tensor. It's going to allow me to satisfy this condition. On every edge, I'm going to put this plus tensor. All right, and let's imagine that's on periodic boundary conditions. Good, and you can see it satisfies both terms. The first one is if you apply x to these indices, you can move x through to the virtual level. So let's just do this on the board. You can move all these internally. And then you have the symmetry of the delta tensor that you can just absorb to the room. All right, so that satisfies those conditions. And similarly, if you have the or z's, you can move these through to the virtual level again. Do that. And now we're going to have pairs around each delta tensor, and the pairs can be cancelled using all the rules out there. So it's the ground state. You got to check it's non-zero, but you can do that. You can just contract this thing and evaluate it. If you see it's non-zero, and I'm not worrying about the normalization. Okay, so there we go. We have a ground state. It's a particular ground state in torus, but like I said, that's not going to be too important for purposes of this talk. And in this model, right, what are the key properties besides the ground space degeneracy? It has this topological order that's characterized by anyons. Because it has a gappable boundary, we don't have to worry about chiral central charge. We think that the full characterization of topological order are just the anyons. A lot of the anyons in this model, pretty familiar to everyone, hopefully. They're E, let me just put all of them. There's 1, E, and psi. They have Z2 times Z2 fusion rules. E times n equals psi, and the rest is everything squares with identity. And you have the generating string operators. Okay. So for E, string operator is just product on the primal lattice. So E in some path, I'm going to call gamma of Z on these edges. So you can draw a path through the lattice and put Z on all those edges. That will create a pair of these. And at the ends, you have this product of like dual edges and some path through the dual lattice on x's. So that will make some M excitations that gets some path on the dual lattice. And the excitations just correspond to like flipping an eigenvalue of these stabilizers. Yeah, all good. And these things have some mutual grading, semiotic grading between each other, but individually they're sort of bosonic. You can check it from the string operators. They commute with themselves. Okay. So how do we see these things in tensor network picture. There's this nice paper, I guess I should, besides this one where they did it for toric code, there's a theory of this for all quantum doubles. That is this nice reference by Norbert et al. I worked this out, and it ends up being related to some virtual symmetry of the tensor network. So in this example, I'm going to ask how do we represent the anyons on the virtual level? And basically, one way of seeing it, and this is supposed to be an example without being too highbrow, is you just take a string operator, plug it into the physical level. So I could put some line of z's through the lattice, and then use these rules to move all these operators to the virtual level. We'll make like a line of z's along the virtual indices. And basically these pairs cancel out along the path because of the symmetries of these tensors in the network. And you're basically just left with one local z at each end. So it's kind of weird because the string operator on the physical level became just a 2-point operator on the virtual level. The other one, the x operator, if you plug that in, you'll see it just moves to like a string operator on the virtual level. So I could sort of have a dual path going between here and here, 2 x's. I have this move that just lets me move it single x's to the virtual level. I can move that there. It turns out the actual path I take doesn't matter in the tensor network because I have this extra symmetry that I can sort of move pairs of x's through this delta tensor. So I can kind of move this path anywhere I like in any state, as long as I don't cross that. As long as I don't cross it with z's, something up to -1. For example, this is equal to the original thing. All right. And sort of in this paper, and following on from this previous work, it's kind of understood that this virtual symmetry of being able to move a string through, and I think you've seen some more general versions of this already today, is the key property of the tensor network representations of these topological states. So here we have basically this Z2 virtual symmetry. It's like a gauge symmetry, if you like. There's some redundancy in the description of the state on the virtual level. Okay, and it has this consequence that because we have this like symmetry, if you just apply some operators to the virtual level and they just disappear, anything anti-commuting with that is going to make this sort of state 0. So it can't be injective. Write that. Let's write the symmetry. Basically, it's like the virtual x's constant path through the dual lattice. And this implies that if I take some region, now I'm thinking about this boundary as being open, and I have this as like a map from the boundary of the region to the bulk. We just write it like that. It's not going to be injective, it's only going to be invertible on symmetric subspace. Because anything that anti-commutes with this is going to make this 0. Okay. So, what does that end up meaning? This is why you can have these sort of local operators in the virtual space that don't pull back to anything local in the physical space, because these z's are exactly the things that don't commute with this virtual symmetry. And only when you have a pair of them do they pull back to the physical space, and they end up being connected by a string, which is why you need to cover some region that touches both points to actually move them to the physical space. Now let's think about the stability of this order. So the actual parent Hamiltonian, toric code Hamiltonian, is known to be stable. And I'm not going to go into this proof at all. Just got to take it on my word. And I didn't write the reference for this. Sorry. So if we add some uniform perturbation to this Hamiltonian, where like it's epsilon's a constant, but small, and these terms are kind of normalized, so nothing crazy is happening, then this result by Mikolakis, I don't know how to spell Mikolakis. Yeah, from some year. Does anyone know what year it is, maybe?
14 maybe? No, earlier.
So there was Bravi and Meetings Mikolakis,
Yeah.
2010.
10.
Was the first paper. But then, the toric code model that
Yeah.
covered that, I think.
It was already known before this paper.
Yeah.
Okay.
It is a commuting Hamiltonian. the non-commuting Hamiltonian is more like a
Yeah, they did the frustration free later, right? And this one's
Right.
commuting.
2013.
So shown by some smart people, this thing is stable, but if you look at these sort of perturbations to the tensor, so you take the building block tensor.
I mean, as you say, they show stability of the gap.
Yeah. Yeah, but I think stability of the gap, add some extra tricks that shows basically stability of the order.
Yeah.
We don't want to go into that. You take this and add some generic perturbation. This thing ends up being unstable. And let me just consider a particular perturbation. So everything that's sort of even under this X symmetry, everything that's even under that symmetry, you can move to the physical level, and essentially it's not a problem. So we just need some generating operator for the odd part, and then we can move the rest of the stuff onto being an even operator and move it to the physical level. It's not a problem. Up to some local unitary that we believe will be the phase. So let's consider a particular perturbation, a relevant one, which is we just apply a single Z. So that'll be odd under this X symmetry. And up to multiplying that with symmetric operators that you can make physical, which aren't a problem, that will give you all the perturbations. And I'm going to consider like uniform local perturbations to the tensor, not sort of correlated. And okay, you can pretty easily see why this causes instability. And there's this nice work that kind of generalizes this picture. By Shukla et al. And the reason is because these things, as I kind of showed you over there, are E anyons. And when we consider this tensor network, so let's put that and make a big state out of it, we're going to get, for like sort of leading order, let's get the same tensor network we started with. So this is the clean one. And then we're going to have some sums. And these things will be popping up everywhere in the lattice. And if we imagine we have closed boundary conditions, actually the first order term doesn't pop up because there's virtual symmetry. It becomes 0 when you have a single one of these in the tensor network. But we get something at second order, epsilon squared. And it is, I'm going to write it like this, EI, EJ. It's like this tensor network with two E anyons inserted and arbitrary positions on the lattice, EI and EJ, with no suppression depending on how far they are from each other. So there's just some like constant in front of it, then we're summing over these things everywhere, and we have higher order terms. And the picture is essentially this is causing some anion condensation. So there's like a finite density of anions hopping around. Essentially when we act on like the virtual level, these anions are not non-trivial superselection sectors because you can just create them with a local operator.
Why is it finite density? There's only two.
There's like further terms. There's all terms. Let's
Well, I guess if you're on a torus, you can just say that at each position with probability epsilon square or with amplitude epsilon, you have an electric charge sitting at any single site, right? With different amplitude. So you have a constant background, but fluctuating constant background charge. So obviously, once you do any braiding, will completely not work anymore, right?
This isn't important. Let's say that was just wrong, and the picture on the set is correct. I'll show you an actual mapping that proves it. So in a second. The picture is, if you buy it or not, it causes basically boson condensation when you add these operators with some small strength in the virtual level. But I think the most convincing thing is if you say, like, what am I doing in the virtual level? This thing is like a trivial superselection sector on the virtual level, even though it's non-trivial on the physical level. So you can just basically destroy these things with local operators. All right, so let's do this properly. Yeah. You can actually, in this case, because it's kind of easy, you do an exact mapping and see that it really immediately gives you a phase transition. And this exact mapping is kind of just re-understanding some old thing, but I'm basically going to explain this in the 2D case, and then it's going to be exactly the same in the 3D case, which is like the new result. And I'm not going to explain it carefully in the 3D case, so if people have questions about the exact mapping, like ask on the 2D one. Before I start, actually, did anyone have more questions about this ground state, or it's pretty familiar?
So could you say again why, if you have something which commutes with the symmetry, it's okay? You can put like as a shallow depth bucket applied to the state.
Right. I didn't like say this carefully. I was kind of skipping over this point. But if you're in the symmetric subspace, you know you're actually this map is like injective on that subspace, so you can invert it. So like basically any operator in that subspace, you could just push on the virtual level, you can just push through to the physical level. And yeah, I was saying something a little bit more subtle. If you have some like other operator that ends up being odd, you can like split it out into a Z part and then some other operator. And you can push that other operator through to the physical level. But it might depend on the position of the anyons, but that's something you can see physically. So controlled on the position of the anyons, you can like apply this extra operator. It ends up just being a big local unitary to do an arbitrary operator on the virtual. Up to having the Z there, it's like just a big local unitary in the physical space plus some Z's on the virtual space, like a generic perturbation. It's kind of a subtle point. You could also just say, let's do a toy model where I consider like the relevant thing that's going to break this.
When you push the thing to the physical subspace, why is it a unitary operation?
Oh, sorry, yeah, it's not necessarily unitary.
But it still doesn't destroy the face.
No, if it's like
Well, you can kick it back onto the Hamiltonian, right? Any local invertible operation on a frustration-free Hamiltonian, you can move it over into the Hamiltonian. So it corresponds to the exact ground state of a small perturbation of the Hamiltonian.
Even if it's not the unitary transfer.
Yes, I mean, I can show you afterwards. It's easy.
Does it need to be sufficiently small?
Sorry?
If it's a big perturbation?
It always
This is-
works.
this is
It's
all
just that
very
at some point it will, of course.
Yeah, this is all like arbitrarily small, but constant. Yeah.
Moving over always works, but obviously the Hamiltonian will only be stable to a certain
Yeah.
length of perturbation. Yes.
Okay, good. So 2D ground state's okay. I'll show you the stability mapping. All right. So. I'm going to use some more tensor identities. The thing we want to think about is going to be some object like I take my perturbed state, let me call like it's epsilon, if that makes sense. It's going to be that tensor there. Yeah, let's call this like A epsilon. Let's do A epsilon. Epsilon is confusing. All right, so I make this like ground state on some torus with this perturbation, and then I'm going to consider something like a autoparameter on the physical space. I guess this is the dual lattice. This is going to be some like closed string operator. That would be like an exact symmetry if I didn't perturb it. So here I want to be like closed dual loop. And okay. Yep. This, hopefully you believe me, this, I'm doing like some special sort of driving a special phase transition where you're going to be able to detect it with the switching of scaling from perimeter to volume law of this operator. That'll make a little bit more sense in a second. So this is the kind of thing I want to consider. So the simplest, this is a generalization of just doing the state overlap. So when I do this sort of state overlap, I'm going to get a whole bunch of like these physical indices contracted, and I'm going to get all these objects. I'm just going to use a little trick on these. That this is equal to this. And then what's the other part I'm going to get? I'm going to have a whole bunch of delta tensors from the two copies. And now they're being contracted over the physical index like this. I've split it this way. I'm going to take one of these halves and move it onto one of the plaquettes and the other one onto the other plaquette. So each plaquette gets 4 of these halves. So I'm going to have objects that look like this. And I'm also potentially going to have some Z in both layers. And they don't have to come together. You could have a Z at the top and at the bottom, as I expand each one out. So, what do you get from this? You kind of check pretty quickly that if there's a Z in either the top or the bottom without there being one on the other side, you're going to get 0. So you get a delta that I is equal to J. And then everything ends up just collapsing. So one way to see this is kind of moving these dualities of the Hadamards onto these tensors from these ones. Then you just have like a deltaing of like two tensors together, and it just sort of collapses them. Like anything that's like an off-diagonal element just becomes 0. So this whole thing, and maybe you just want to believe me, just collapses into this. And I'm also going for convenience to change the basis on this. I probably should have just started in the other basis. But I can switch this to the other basis, making this an x, with this change of basis. And actually here there's some like proportionality. Okay. But we're going to get a bunch of proportionalities I'm going to argue that don't matter. Okay, so this is the basic trick I need. People want to believe it or ask me questions about it.
Can you repeat again? Which is the observable you take? This.
What is it? Oh yeah. I'm going to come back to this, but we're going to use like a closed dual loop of like the x. It's going to detect a condensation. Yeah, it's possible. Like, check the paper. Okay. So let me here a little bit. I'm going to define some tensor. So using this trick, I'm going to have basically collapsed my whole sandwich. And let me write it like this into like this 2D sort of partition function. Maybe it's worth doing kind of a good picture here. Let's imagine boundaries again. This thing is just equal to my sort of, my tops contracted with the bottom one. Cross edges contracted. That is a big sandwich, and I'm just collapsing it into like a I'm just collapsing it into a partition function. Good enough. So yeah, and let's just do the case where there's no operator in the middle. So this is just like the overlap. This is this. And these tensors have some like 1 plus epsilon z everywhere. Because I've added the perturbation.
So I guess it needs to be epsilon squared if both these.
Good point. So I actually used a kind of funny notation for that. Let me tell you what this actually is. This is going to be exactly just this plus 1, because I change basis, plus some epsilon squared, because whatever perturbation I had doesn't have to be real. I get like conjugate in the overlap from the bra, and they'll just give me absolute value squared. This the whole thing sort of actually not important. That's important. Okay. So with epsilon squared, I get this term. And this is like basically the thing I'm trying to evaluate, the partition function given by that guy everywhere. And the trick is basically just to say, all right, up to like epsilon, this is just some e to the minus beta, function of epsilon. And this sort of unmessed up one plus e to the beta of some messed up one. Okay. Where how is e to the beta defined? By this. Okay, is that fine? And then I'm going to rewrite this in a more familiar way, where I basically just change these. I assign some kind of variable to each of these links. So let's do it somewhere. Let me draw this first, then I'll draw that. So you have kind of sigma variables on all the edges. And I'm just rewriting this kind of conditional thing in terms of looking edges touching the vertex. These sigma e variables. And what are these sigma e variables? I have this tensor. I'm just calling these things like sigma e north, sigma e west. Okay, so hold these variables so they can look a bit more like a spin model, classical spin model. And I've basically rewritten this tensor as a function that just depends on the surrounding variables of some each of the minus beta Hamiltonian term. Right. So when I look at evaluating the whole tensor network, let's go back to this thing I wanted to work out. And yeah, we have to say the slide where we stick in these x's. The x's just move directly to like a physical level, and they just become a product of these sigma variables. This thing is just going to be up to a factor, proportionality constant, sum over all of these sigma edge configurations, not just the local ones around one tensor. And then we have e to the minus beta h times the sort of spin version of this operator. So this is just some classical expectation value. At temperature beta. What's the Hamiltonian? It's just some overall vertices, product of sigma on the edges touching the vertex. It's just like 2D lattice gauge theory, lattice gauge theory. So I just have this expectation value in Z2 lattice gauge theory at some finite temperature determined by the perturbation strength. That's like the main argument. So does that make sense? You want to ask questions about this mapping? And just use some tensor tricks to rewrite stuff as a stat-mech partition function in the overlap. And the idea is...
So this is periodic boundary conditions? Or is it
I'm doing periodic boundary conditions. I think that was actually not so important.
Yeah.
But let's say it is periodic boundary conditions. It actually might introduce a little bit of complication to periodic boundary conditions. Okay, so the idea is now we have this expectation value of this operator that's going to tell us when there's a phase transition. So this Hamiltonian, finite t phase transition. Detected. Sorry, I'm still in 2D. 0 t phase transition. Detected by the crossover of this stuff from a boundary of a region to exponentially decaying with the bulk of the region. If, let's say here, basically, R is some region bounded by this curve that's closed. So it does say it's homologically trivial. Good. Yeah, and so the point is here it happens at 0t. 0t maps back to 0 epsilon. So we see this phase transition measured by like an autoparameter in the toric code. So this autoparameter, I think it's kind of important to really see this actually works. You're not just like mapping something randomly and then saying that thing has a phase transition. The autoparameter that detects a phase transition there maps back to one that detects a phase transition on toric code when you have a certain kind of perturbation. So you see there's some phase transition in toric code detected by an actual autoparameter in toric code that makes sense. And it happens when you add like an arbitrarily small perturbation. That's one. And constant strength.
nothing happens in the normalization.
In the normalization, yeah, like the normalization is kind of getting messed up. Like you need to have
It's just, you're not done with it, but
it's
nevertheless,
yeah, I think
just want to know that.
you could do this just as the mapping and say like the partition function seems to diverge, but it's a little bit confusing to try and detect a phase transition that way because that could from some
No, but I
normalization.
mean, yeah. You say proportional side of this thing. You want to make sure that the other factor, e to the minus r.
Oh yeah, like these don't come from normalization. I really should probably be like dividing by something that kills this. And then you maybe should be a bit more cautious about the limit of the epsilon go to 0, but I think that's not a problem.
Okay.
That was a bit sloppy here. I probably should have divided by some normalization actually to get from the left to the right because the tensor network was actually normalized, so I should really have this in the bottom.
And it looks like it is essentially independent of the size of the torus.
Yeah, yeah. It just happens at arbitrarily small constant epsilon. Good. So that's the story about 2D and how you see it kind of really works beyond this sort of picture that maybe you don't buy about the anion condensation. Oh, and here actually you don't just have to rely on some previously. It's really easy to solve this. So you actually can exactly find that the scaling immediately goes like this thing's actually like tan beta to the r. You can just calculate it. Okay, and now I want to tell you about 3D. Probably won't get to the point. Yep.
Guys, I am a little bit confused. It should be 1, right? For epsilon equal to 0. There's nothing.
Yeah, it's 1. Should be 1 for epsilon equal to 0.
But then, but it's e to the minus boundary of r.
Oh yeah, there's some constant there. It's going to be like error.
Oh, okay.
Yeah, it's a bit degenerate, the case where it's exact. And it's also kind of this another subtle point I'm glossing over is like we're doing a certain kind of phase transition here where this order parameter works. It doesn't work with a generic perturbation, but we're doing like a perturbation where we're only connecting one type of anion. And so one of the symmetries kind of stays good, and you can use the other one as an order parameter for its phase transition. If you really perturb generically, you have to worry about using, to actually see this kind of crossover, you've got to use the right string operators. But in this case, we're doing a very special kind of phase transition where we don't break one of the symmetries of the toric code, and that's why we can use this. What quickly say about 3D. So really, it's like the same game. The only difference is that the, let's say, x versus z basis for the toric code not equivalent now. So before I did this in one basis versus the other, and you could have asked, like, what if I work with the other basis, and this is sort of a simplest example of one of these bimodules we saw earlier. And it ends up being just like, almost exactly the same up to some local basis change in this case. The two different ways of writing it, essentially. In 3D, it's not the case. So you really make a choice of which basis you're going to kind of use for the ground state. And one generalization is basically have your delta tensors on the vertices. So I'm not going to draw the lattice now because it's too difficult. I'm just going to draw your unit cell tensor. So now you have like one of these delta tensors with more legs. That's the same object basically. And these plus tensors with the same number of legs. And this is going to, you can show this as the ground state of, tensor version of this. Tensor network version of this is the ground state of toric code written in this way, where I have 1 qubit per edge of a qubit lattice. And let's imagine periodic boundary conditions again. Okay. And you'll see if you kind of play with this one a little bit that it ends up having kind of a codimension 1 symmetry again, and everything's very similar to 2D. So it has these like virtual sheet-like symmetries, and basically a local excitation, a local gauge charge, like is created by this like local Z operator on the vertical level. So again, when you like add Z perturbations, you can essentially induce this like anion condensation. Well, it's not really an anion anymore; it's in 3D. It's just a boson. You can induce this boson condensation with an arbitrarily small perturbation. And for these ones, for these kind of toric codes, when you write them down with code dimension 1 operators, you can always exactly like compute this mapping because it's very easy. And you find that you get a phase transition at 0 perturbation strength. So this one has the same stability problem. I'm glossing over it because it's not really interesting, nothing new happens. And if you write these toric codes of this type in higher dimensions, you'll have the same problem. Luckily, when you go to higher dimensions, you get more types of toric codes, and the bases aren't always equivalent. So essentially, every other toric code, besides this exact one where you get codimension 1 symmetries, we think will end up being stable. So let me tell you.
That one will not exactly map to then a 3D classical, a 3D lattice gauge.
It's just like a higher form lattice gauge theory. It's something people don't study, but it's just crap. It's like a crap model.
This one should map to something with like an icing symmetry at the boundary, I guess, no?
Yeah, it's got a global symmetry at the boundary, but in the bulk, it's like got some kind of like one, codimension 1 gauge fields or something instead of, it's like sheet-like instead of string-like. Oh, actually, yeah, sorry, I'm saying it in a way more confusing way. You could do a duality, it would exactly be an Ising model. No, actually, that can't be true. It's not crappy lattice gauge theory that's too high form to have the phase transition. Let me show you the interesting one. This one's boring. Or we're out of time. Yeah, so this one's a bit harder to draw. Still the same building blocks. So now we have this funny thing. Let me try and make these physical indices squiggly in this case. This is like some big blob tensor that has like 3 physical indices and like 2 virtual indices for each direction. But now it's in 3D, so there's like 3 going in and out of the tensor. And this is basically just the ground state in the other basis. But if you like, I'm writing it so this is a slightly different Hamiltonian to really make the choice clear. I'm basically just doing a hand-of-hard on physical indices and applying my recipe. The X thing becomes symmetry. So really, this is changing basis. That's what we're doing. Good. And so now this thing, this model ends up picking up again the X physical operators become into virtual symmetry. But in this case, these X string operators form a, I'll say, you get a Z2 2 symmetry at the virtual level, given by any products of edges in the lattice of XE on those edges, a closed path. So this has got codimension 2, that's like this notation people use for higher form symmetries. And the really new feature about this is that now you get some local constraints. So if I take the symmetry, this virtual symmetry, and I apply it on every face around the cube, maybe I should draw a picture for this. You can imagine I have some cube, and I have faces. Back one. If I have this sort of symmetry around all these faces, when I contract these things up with these kind of plus tensors, this is getting a bit hard to draw, but basically every pair of these edges gets contracted up with some plus tensors. Alright, these plus tensors have some symmetry that the x's can move through them. So this ends up being equivalent to just do nothing. Like, there's two ways to delete this this product of X symmetries. This gives you a constraint that if you have like a single Z on some vertex, like locally on a single cube, if you don't pair that up with another Z, you just get 0. The ground state just gives you 0. So not only do these Zs have to come in globally in pairs, which was the case in 2D, which is why we only saw epsilon squared order coming into this sum, locally, the Z perturbations on the virtual level have to come in pairs. So when you kind of write this perturbed ground state, we have this kind of A epsilon, we're going to be able to write A naught plus some sum over like lengths, epsilon to the length, and then there'll be some like string excitation. And it's going to be the sum over all strings in the lattice, string excitation of length L. Okay. So here, the big difference is there's actually some suppression of these string excitations with the length.
Is that completely hand wavy, or is that somewhat formalizable?
This thing? I mean, if you just expand this out, like, this is what you'll find in this.
So this
This is not what you use to prove that it's actually stable, though. It's just a picture.
but it's a sum over configurations of strings, or?
Yeah, all kind of configurations of strings. So it's a bit pretty crazy. You can't really use this.
Well, I guess I asked, in the other case, you can easily see that under RG you flow away from the point you're at, right? You take two perturbations, epsilon, which give an odd parity, then the total weight of odd parity is 2 epsilon. And I was always wondering if in this picture one can find a similar hand-wavy RG argument that you should flow back. But that's not like that, right?
I
That's
can just expand work, yeah.
Exactly.
Well, this probably means there's a cluster expansion of this third state.
I think it would be nice to see this in a somewhat more formalized way, maybe not really rigorous or only for a specific instance. Also to see where these kind of broken Z2 symmetries maybe come back or don't come back in some expansion. Anyway.
Yeah, I think, what can I say about this? It's still not obvious from this, though, like as you're saying, whether there's a phase transition.
I was hoping. It's just
because like, it's not like you're getting, if you were doing a physical perturbation, these would come in at like epsilon to the bounding membrane of the string. Epsilon to the power of the bounding membrane of the string, not epsilon to the power of the string length. So it's like getting much less suppressed than it would be by a physical perturbation.
So, and is it absolute to the L, or it's a factor of absolute to the L for each string?
I'm writing like some sum over strings of like length.
Right, so there's a product over
Or
all the strings of epsilon to the.
Yeah, I mean, this should be like, this could be disconnected strings. They could be each be of length L.
Right, but each would have their weight epsilon power.
Yeah. It's just like the total string length. It doesn't matter if they're connected or not. You could probably do some connected component expansion and then, I don't know. This is really not the way I did it. This is just, I'm just trying to give you some toy picture.
Okay.
This one, it does seem like it's trying to fluctuate around the loops, but they're actually suppressed. That's the point of this toy picture. But again, you can do the exact mapping, and it's like, basically, it's almost exactly the same as before. You use the same tricks, because you see the objects you're dealing with. You have these plaquette delta tensors, and when you perturb, you just put basically like a Z on that plaquette. Those are your like odd perturbations. And when you go through the mapping again, you just get, I'm not going to explain it again in full. Just think of it as like direct generalization of the previous one. The recipe there applies to anything built out of like delta and plus tensors. You can just push through this mapping when you have these perturbations of Z on the deltas to get some spin model, and the structure of the spin model, like what the interactions are, is just determined by the original tensor network. And the thing we're going to look at again is exactly just X. So loop operator. This is like 3D now. This is like the perturbed 3D to code ground state. And if you follow the recipe that I sort of did for 2D there, you get exactly again that normalizing this whole thing. On this side, it's just a product of spin operators. Closed loop. Okay. 3D, so 3D is E2 lattice gauge theory. So hopefully you'll believe, if you believe this one, that will end up being 2D lattice gauge theory. This is like exactly the same mapping, except you're just in 3D now. You get 3D lattice gauge theory. It's not so surprising. But the point of this, the outcome of this mapping, is that this has a non-zero T phase transition. And again, detected by the scaling going from, I'm just going to write perimeter to area. Okay. And again, it's kind of important that you're like preserving one of the symmetries of the toric code to have this operator be a good order parameter for the phase transition. Yeah, so really the same trick, but this time the thing you map to just has a non-zero temperature phase transition. This maps back to like a non-zero perturbation strength phase transition. And you can kind of be a bit more careful and check like the the other operator is exactly preserved. So if you want to define toric code by having kind of perimeter law under these two commuting sets of intervals, then this state is really the toric code ground state still. So it's sort of funny. And so okay, we should say one word. When you go to 4D, you can write down a basis. You can write down this toric code that's sort of living in the middle dimension, where both bases have this kind of higher form symmetry, and they both end up being stable. So in 4D, we expect, I guess, that like the conjecture is like all ways of writing down, all reasonable ways of writing down 4D toric code will actually be stable. In 2D, none of the ways of writing down the 2D toric code that we know of are stable. In 3D, you kind of have this choice of basis, and it's a bit strange. Which basis you choose determines whether you're stable or not. So like and I guess these tensors being stable, we think will end up being related to whether you can actually kind of find them stable in numerics, or whether, if you're trying to do some numerics and you hope you get some topological symmetry kind of emerging, if it gets kind of broken and the phase disappears with an arbitrarily small perturbation, that's not very good. Here, I don't know what this really means, because like, if you're kind of, if your algorithm's converging onto this one, it's crap, but this one is quite good. I don't know if that means you'll find this one better than this one. I have no idea. So maybe someone who knows more about how numerics works could tell me some good ideas about that. I'm not going to say anything about 2D models. I'll say last thing about 3D. So in 3D, there's a whole bunch more topological orders, and the expectations we have, say conjectures based on this, is that for any of these like fracton kind of orders that exist in 3D, they always kind of come with only point particles if you take the usual definition of fracton. So we expect that they're all unstable any way you represent them. And if you take these obvious representations, you immediately see they're sort of unstable to small tensor perturbations. And then we expect for sort of lattice gauge theories that there should be like the rep basis will be stable, essentially. That's like the generalization of this basis of toric code being stable, but we didn't show that. Yeah, good. And I want to end with, okay, so that's the main result, this 3D toric code is stable. And then we have I have some questions. The 2D one is not stable, but by having this 3D bulk, we kind of become stable. And there's this kind of idea from measurement-based quantum computing where you kind of fault tolerantly repair the boundary state by using an auxiliary 3D bulk to measure away. So can we do like a 2+1D tensor network, maybe that's still kind of efficient, like a mirror, a 2+1D mirror for a boundary 2D state, would that be stable? That's my open question, and I'll end with that. Thanks for your attention.